In this section, we will be looking at Newton's second law of motion. Before we look at Newton's second law, we need to understand certain terms first. The first term we need to know is linear momentum. Linear momentum, symbol P, is defined as a product of its mass and velocity. Simply put, P equals to m times v. Right, this is in the learning outcome D. You need to be able to define what is linear momentum. You need to use a formula to solve questions. Suppose on a sunny day you were dancing on a field. Suddenly, a hippo comes charging at you. Will you be scared? You will be so scared that your shirt and yourself turn blue, right? Okay, let's see. Maybe on another day, another sunny day, you are happily dancing and a rat appear. Will you be scared? Of course, who is not scared of rats, right? Now, which are you more scared of, the hippo or the rat? For many of you, it's the rat, right? Because they run so fast and they are dirty, right? But which does more damage when they hit you? Of course, it's the angry hippo. If you say the rat, I think you got brain damage, right? Why? Why does the angry hippo do more damage? We all know because it's much bigger, it's more tuatia, right? But in physics sense, we say it has bigger mass. Why bigger mass will cause more damage? Because bigger mass have bigger momentum. Let's look at another scenario now. Okay, now we have the rats and we have flying bullets. Which one will do more damage? Of course, it's the flying bullet, right? Unless you tell me you are Doraemon, then you are more scared of rat. Why does a bullet do more damage? Because momentum, as you can see from the formula, is not just dependent on mass. It is also dependent on velocity. Bullet, although has a smaller mass than the rat, but its velocity is so much higher, so it has a greater momentum. Now, we almost think that when you have greater momentum, you will have greater damage. That is not entirely true. To be very specific, it should be the rate of change of momentum, and it is proportional to the net external force acting on a body. And this rate of change of momentum will be in the direction of this net external force. We can now use this Newton's second law to define a force. Right, a force on a body is now defined as the rate of change of momentum of a body, and it acts in the direction of the change in momentum. So you cannot say a force is a push or pull anymore in A level. We demand a more scientific answer. So you should be able to now state the last of Newton's law. So you have seen Newton's first law, Newton's third law, and now Newton's second law. You must memorize them and state them correctly. Take note of the keyword. Example, net external force. And you should also learn the learning outcome F. That means you should relate the net force to the rate of change of momentum. Let's look at work example 3 on page 5. A ball of mass 58 gram travel at a velocity of 30 meter per second, hits a wall and rebounds at velocity of 20 meter per second. Calculate the change in momentum of the ball. Okay, so initially it's 30 meters per second to a right, and finally it rebounds, so opposite direction, 20 meter per second. Okay, first thing first, we need to decide which direction is positive. So I will take rightward as positive now. So the change in momentum will be the final minus initial. In physics, change always final minus initial. So I use a final momentum, which is the mass times final velocity minus the initial momentum, which is a mass minus the initial velocity. Right, so the mass is 0.058 kg and v, the final velocity, is negative 20 because I have defined rightward as positive. Since v is towards the left, it is negative. So the product of mv now minus mu. Okay, u is moving to a right, so it is positive 30. So calculate this, you will find that the momentum is negative 2.9. So momentum is a vector. So the sign of the direction is important, which is why you need to state which direction is positive. Now, what does negative 2.9 means? Right? The negative sign implies that the change in momentum is towards the left. Because the right is positive, so you get negative, means it is towards the left. So the force on the ball is to the left. It is not difficult to understand this because the ball hit the wall, and so the wall should push it towards the right, towards the left. So the force on the ball is to the left, therefore the change in momentum is also to the left. Work example 4. A toy boat of mass 100 gram changes its velocity from 8 meter per second due north to 6 meter per second due east. Calculate change in momentum. Remember, momentum is a vector, so the direction is important. In this case, one is moving towards north and one is moving towards east. Right, so remember, change in momentum is final momentum minus initial momentum. So minus initial momentum is same as adding the initial momentum in the reverse direction. So you have the arrow being reversed in the second line. From these two arrows, now I can draw a vector diagram. And the resultant is the hypotenuse, which found to be 1 kg per meter per second. Right, and we can find the angle using tangent 0.8, tangent 53, tangent theta equals to 0.8 over 0.6. So you can find theta. This is in chapter 1, so I will assume you know. Right, so after this, you find the angle to be 53 degree. You can either describe it as south of east, or you can find the other angle, adjacent angle, and use 37 degree east of north, east of south. All right, now let's look at mathematical statement of Newton's second law. Right, in words, we say that the rate of change of momentum is proportional to the net external force. So if we write it in terms of mathematical symbol, this is what we get. So because it is proportional, I can use an equal sign and use K as a proportionality constant. Okay, now this K, the value of K, it actually depends on how I define a unit of force. If we choose to define unit, which is Newton, unit of force, Newton, as the force which causes a mass of 1 kg to have acceleration of 1 meter per second square, then I get 1 Newton is equals to K times 1 kg times 1 meter per second square, and hence K becomes 1. Right? So it is for such convenience that we define Newton as such, so that the K, the proportionality constant, is 1. Therefore, now it is a simpler form, just F net equals to dmv dt. Okay, now let's look at page 6. If a net force acts in the same direction as the velocity, it will actually accelerate the car, right? We learn in kinematics, same direction, force, same direction, as v, so it will accelerate. So we can say v increases, therefore momentum increases because momentum is mv. Now, if the net force acts in opposite direction to the velocity of v, the car is moving forward, but there's a backward force, maybe when you're braking. Right, so the velocity should decrease. Therefore, the momentum should decrease. This is a deceleration. Let's look at work example 5. If a tennis player plays a ball of mass 58 gram, which reaches her with a velocity of 20 meter per second, if the maximum force she can exert on the ball is 200 Newton, what is the minimum duration of the ball must be in contact with the racket in order for a player to return it to her opponent with a higher speed now. Okay, this diagram will help us understand a little. So taking leftward as positive, F equals to the mv dt, which means it is actually mv minus mu. Okay, since m is constant, I can bring out the m, so it becomes v minus u over t. Now, substitute the values that I know. The force, maximum force that the tennis player can exert is 200, so F net equals 200. The mass is 0.058. Now, what is V? Okay, if we say leftward is positive, when I return the ball by the racket, it should be towards the left. So that is positive. So V minus U, and U is negative because it is moving to the right. So I have V minus negative U, negative 20. Okay, so you can find the time from here. Right, this is a learning outcome G. You need to remember the relationship F equals to MA or F equals to the mv dt and solve the problems. Okay, now assume we have two trains which have the same mass traveling with the same initial velocity. Who is stronger, Superman or Spider-Man? You look at the GIF, you can see that the Spider-Man is almost being pushed together with a train, trying hard to stop it, right? Whereas the Superman actually stop it rather quickly. So since the change in momentum is large, okay, both have the change in momentum because they have same mass and same initial velocity, and the final velocity is 0. So a large force is required to stop the train. But Superman stops the train in a shorter time. So the mv is the same. That means the change in momentum is the same for both Superman and Spider-Man. But because Superman stops it in a shorter time, he exerts a larger force. So he is stronger. So in this formula, we can see that it is not just the change in momentum that determines how big the force is. It is also the time duration. The shorter the time, if you can stop something instantly, you need a bigger force. The converse is also true. If we can lengthen the time where the change in momentum happens, then the force will be smaller. Right? This is actually the basic principle behind cushioning an object. Right? When you are hitting the wall, for example, if I put a mattress on the wall, you won't feel so painful because you take a longer time to stop. Or when we land, after jumping, we flex our knees to reduce the force and reduce the injury. You look at the cat, right? Actually bend its knees, and so that the time taken increase. So F net equals the mv dt. Since time increase, so F net will become smaller. One of the system is a system of constant mass, where velocity is the one that change. So we can use the definition from Newton's second law, F net equals the mv dt. Since m is constant, you can bring out. So we left with m dv dt. And since dv dt is acceleration, right, so F net equals to ma. So this is how you get F equals to ma, which you learn in secondary school. Remember, F net is the net force, or we call resultant force. A resultant force means you add all the external force and find the resultant of all these forces. So that is called the resultant force, right? And take note that the acceleration is always the same direction as the net force. How do we apply this formula? In O level, it's quite simple. In A level, the problem is more complex. So let's look at some steps to do so. First, you draw a free body diagram. Supposedly, we have a ball in the air. It is acted by the Earth, so it has weight W downwards. Let's say it is moving downwards with a velocity V. Because it is moving downwards and air resistance is not negligible, so it is going to experience air resistance, which is upwards. Air resistance is always opposite direction of velocity. Step 2, so I have drawn the free body diagram. So step 2 indicate direction of the acceleration. If the direction of the acceleration is unknown, you can just assume it in any direction that is logical. In this case, it is either upwards or downwards. If the final answer turns out to be negative, it just means that you have assumed to be the opposite direction. Okay, next step, resolve all forces along the direction of the acceleration. Cancel the word into in your notes on page 7. Resolve all forces along the direction of acceleration. Step 4, substitute the values into F net equals to ma. Remember, F net is the vector sum of all forces. As a rule of thumb, when you apply this formula, you will keep all the forces on the left-hand side of the equation. Take note of the sign, whether they are positive or negative, and put ma on the right. So like this, in this example, taking downwards as positive. mg, the weight is downwards, so it's positive. R is upward, so it's negative. Right, so we have mg minus r equals to ma. The forces are on the left-hand side of the equation, and the ma is on the right-hand side of the equation. Okay, so this is the same learning outcome G. You need to recall and solve problem using F equals to ma. Next example, we have 20 kg wagon is put along a level ground by a rope inclined at 30 degrees. Right, so the wagon is being put by a rope at an angle, and there is a friction that opposes the motion. How large is the pulling force X if the wagon is moving along the ground with acceleration of 0.4? So step number 1, remember, draw the free body diagram, draw all the forces acting on the wagon. You do not need to draw a wagon. Any object, you can replace it with a small circle. Okay, so there's a pulling force 30 degrees to the horizontal. Right, now assume a direction for acceleration. Okay, I'll assume it to be the right, and I'll take rightwards as positive. Now, next step, resolve forces in the direction of the acceleration. So X was at a angle 30 degrees. So now I find a component of X in the direction of acceleration. So that's X cosine 30. Both the forces that are perpendicular to the direction of acceleration, we do not consider them. These two forces are the normal reaction, which is upwards, and mg, which is downwards, and also the x sine 30, okay, which is the vertical component of the tension in the rope. Right? So now the fourth step is to apply the formula. So F net equals to MA. So towards the right is positive. So x cosine 30 is positive. Friction is negative. Right, so substitute, put all the forces on the left side, MA on the right side, substitute the mass and the acceleration, and you can calculate the force X. Okay, part B. If the wagon moves with a constant speed, what do we do? Constant speed means acceleration is zero, right? So actually there is no direction of acceleration here, so I'll just let rightwards as positive. So I can put into the formula again, F net equals to MA, X cosine 30 is to the right, so it's positive. Friction is negative, so it's negative 30. Friction is to the left, so it's negative 30. So on the right hand side of the equation, A is 0. So right hand side is 0. So solving this, we get X equals to 35. Right, so you can see earlier X is 44 Newton when we have an acceleration to the right. Now it is only 35 because it doesn't increase the speed of the wagon. It need not be so big, so it is a smaller value, 35 Newtons. Right, and same, this is the learning outcome of solving problem. We'll now look at example 7, apparent weight in a lift. Now, what is apparent weight? Apparent weight refers to the force a person acts on the surface she's standing on. Right? It is numerically equals to the force that the surface acts on her. Right? And this is an example of action-reaction pair. So it's numerically equals to a normal reaction force. So whenever we are told to find apparent weight, we actually just find the normal reaction. Okay, let's watch this video to get a better idea.
For our experiment, we're going to demonstrate Newton's second law, force equals mass times acceleration, with an elevator.
Mass is absolute, whereas weight is not, because it's dependent on the acceleration of the body.
As the elevator begins to go upwards, our acceleration in this inertial frame will be greater than the downward acceleration of the elevator. So when acceleration increases, the weight will increase. When we get to the top of the elevator ride, the elevator will slow down, which means our upwards acceleration will be greater than the inertial frame of the elevator. When acceleration goes down, weight goes down.
Kelly is currently on the scale. We're on the second floor, and we're going to move up to the third floor, and his weight should increase and then decrease.
Wait.
Oh, baby.
We are now going to do the experiment of the elevator moving downwards. When it starts to move, it accelerates downwards, and his weight will decrease. And then as we reach the floor, it will accelerate upwards as it slows down, and his weight will increase slightly. His weight should decrease and then increase.
So we just proved that weight is dependent upon acceleration, and it can be shown in this elevator. Now we're going to head over to another elevator.
Isn't it very strange that the weighing scale gives different reading when the lift is moving upwards or downwards? Right, so it tells us that the weighing scale does not actually measure your weight. Your weight shouldn't be changing when the lift is moving up or down. What the weighing scale is actually weighing is how hard you are pressing on the scale. In other words, it will be numerically equal to the normal reaction by the scale on you. So the contact force of you on the scale is equal to the contact force of the scale on you. Now let's look at this example. So first step, you need to draw free body diagram. Area weight is acting downwards, her real weight, not apparent weight. Okay, and there's a normal reaction by the weighing scale on her because she's standing on the scale, so the scale is supporting her, so there's an upward force by the scale. So we resolve the forces vertically, right? And using Newton's second law, you can see that the force area pushes down on the scale, that is her apparent weight. It must be equals to n, the normal reaction. So we can calculate n to find her apparent weight. Part A, if the lift is moving upwards with a constant speed of 4 meters per second, and we take upwards to be positive, so assume a direction, apply the formula. So n is upwards, and so upward is positive, so n is positive, mg is downwards, so it's negative. Right, so since it is moving at constant speed, so a equals to 0, so the right hand side equals to 0, m minus mg equals to 0, so n equals to mg. So apparent weight equals to n in magnitude, so we can calculate the apparent weight, okay, which is equals to mg. In the second scenario, the lift is accelerating upwards. Okay, so take upwards as positive. So F net equals to MA. So N is upwards, so N is positive, Mg is downwards, therefore it is negative. So substitute in the values, move Mg over to the right hand side, and you can find N, which is 591. The lift is decelerating downwards at 2 meters per second square, then it will cause the same apparent weight as B, because we'll take downwards as positive, so mg minus n equals to m times negative a. So they will give the same value. Okay, let's look at part C. Okay, part C, the lift is accelerating downwards at 2 meters per second square. So now I take downwards as positive. Okay, sorry, the diagram is wrong. You should take downwards as positive. So mg minus n equals to ma, and n equals to mg minus a. Right? So substitute in the values, you find that the apparent weight now is 391, which is smaller. If the lift cable snaps, the whole lift will fall. Right? So I take downwards as positive. Ignore the diagram direction is wrong, so downward is positive, so F net equals to MA, so mg minus n equals to MA. Right, so you can find that because the lift is free falling, so the acceleration should be g, so MA equals to mg. So in the end, the normal reaction is 0, so apparent weight is 0. This is because you are free falling together with the lift, you are not pushing down on the weighing scale because you are falling together at the same rate. Okay, so you are supposed to be able to solve this problem. Okay, now let's do another check. Use Newton's law, explain why the cart moves. In the first instance, where the fan is on the cart and then there is no sail. For the cart without the sail, the fan blows the air to the left. Right? So the fan blows the air to the left, exerting the force on the air. By Newton's third law, the air should push the fan to the right at the same time. These are action-reaction pair. So force on air and then by fan, the reaction pair will be force on fan by air. Now, if these two forces are equal, why did the cart move? Shouldn't they cancel out each other? Because these two forces are acting on different body. So you should not think that they cancel out each other. They don't. One force is acting on the fan and one force is acting on the air. So even though there are two forces, there is only one force acting on the cart, which is the force on fan by air. This should reinforce your understanding that Newton's third law is for two different bodies. Since now I'm only interested in the cut, I am looking at only one body. So I should just look at the cut, or in this case, the fan. So I should consider the force on the fan, not the force on the air. Okay, I hope that is clear. Let's look at another kind of scenario we call the connected bodies. Okay, in this case, it is a horizontal motion with a tractor pulling a trailer. So the key concept is this. All individuals' body are connected in this kind of question, and so they always travel at the same velocity and same acceleration. If we consider this tractor and trailer as one single system, that means you think of it as one body, don't consider them separately. The tension between the rod becomes internal forces. Okay? Because they are act within each other. External forces must be from external body. So this, since we consider them as one body, the tension becomes within the body. So they are internal forces. And you should not use them in F net equals to MA. Okay, so part A. Consider tractor and trailer as one system. Notice the tension acting on the tractor and the trailer are not included because they are internal forces. So now we represent this one system with one ball. Okay, in free body diagram, you can always represent a complicated body as one ball. So it is acted with a thrust towards the left, okay, that push it forward, and then a friction backwards, okay, and a weight downwards and normal reaction upwards. Taking leftward as positive, okay, so follow direction of the acceleration. Thrust minus total friction equals to 5,000, the mass multiplied by acceleration. Right, sub in the values, you can find the acceleration. So acceleration is positive, that means it is in the direction of the thrust, which is to the left. Right, notice we did not use normal reaction and weight in this equation at all because they do not have any component in the horizontal direction, which is the direction of the motion. So they have no contribution in causing the trailer or tractor to move in the horizontal direction. Okay, let's look at part B. If we want to find the tension in the tow bar, now I should consider trailer and the tractor separately because you are considering a internal force, so you must make sure it becomes external force. It only becomes external force if you consider the trailer alone or the tractor alone. Okay, in this case, the trailer is not acted by the engine thrust. The engine thrust acts on the tractor, and then the tractor pulls the trailer along with tension T. So on the trailer, in the forward direction to the left, it is only acted by the tension in the tow bar. Okay, so apply F net equals to MA. Again, take leftward as positive because that's the direction of the acceleration. So the F net, put all the forces on the left hand side, so it will be the tension minus the friction equals to M2A. Okay, A you have found earlier, so you can find the tension. Okay, remember the tractor, trailer all move with the same velocity and same direction, whether it's separate system or one single system. When you consider them, they will still have the same acceleration. We can also solve the same question by using only tractor. Okay, you can try that in your notes and compare and see if you get the same tension. Okay, so this is the learning outcome. Let's look at the last example for this chapter. Okay, in this example, we have two blocks connected by inextensible string. So inextensible string means that the length of the string remains the same, right? And in this case, it's frictionless pulley, so here there is no friction. And the plane are also frictionless. Okay, what is the key concept in this solving this kind of question? Okay, for these questions, we can consider each mass, each of these, as a separate system, or you can consider the whole thing as one system. Okay, next is to assume a direction and keep it consistent. So I can assume that it is accelerating upwards here. If this is accelerating upwards, then this mesh should move up and this mesh should move down. Okay, likewise, I could also assume that it is accelerating in the opposite direction. So for example, I can assume that it's accelerating downwards here. So in this case, 50 kg mass must be accelerating upwards. Okay, let's consider the 100 kg mass. Remember step number 1, draw free body diagram. So once you have drawn the free body diagram, decide where is acceleration. Okay, so we have assumed upwards, and this is the direction of acceleration. T1 will be positive, m1g sine 30. How do I get m1g sine 30? I'm looking for the component of mg. Okay, so mg can be broken into these two components. So the component that I'm interested is this one, because it's along the direction of the acceleration. How do I find this number, right? So I can see that this is 30 degrees, so this must be 60 degrees. Okay, and so this must be 30 degrees. So if I redraw the triangle, it will look like this. So this is 30 degrees. This is mg. So I'm interested in this length. Okay, this length and this length is the same, right? Okay, so this is my mg sine 30. Okay, remember the one that you resolve must always be hypotenuse. So you will draw this as the longer side, then you do this way. Okay, there are some students who do this way. This is wrong. This is not resolving correctly because the mg must be hypotenuse. Okay. Okay, so the tension is upwards, so it's positive, and m1 is 100. Okay, so it's mg sine 30. This is negative because this is mg sine 30. So it is in the opposite direction of A, so it is negative. Okay, so we form one equation. Okay, do the same for the 50 kg, right? And since A here is positive, now A must be this way positive. So I form the equation m2g sine 53. Okay, how do we get this? Can you go and derive? Pause the video and derive. Okay, now I will show you how it is derived. So remember, this is 53 degrees. Okay, why is this 53? Because this is 90 minus 53. Okay, and this is 90 minus this 90 minus 53, so it must be 53. So from here, resolve. This is triangle. MG should be the hypotenuse. So I'm looking for this length. Okay, so this is M2G sine 53. Okay, this length is also same as this length. Okay, so this is mg sine 53. Okay, so since downward is positive, mg sine 53 should be positive and T2 is negative. Okay, remember, since this is the same string, if it's the same string, then the tension should be the same, right? So it is the same tension, sub in T2 equals to tension T. Now you have two equations, solve them simultaneously, you can find T and A. Since A is negative, that means we have assumed wrongly. So actually, this is the correct A direction. Okay, but it doesn't matter. Now I've found that it's negative. I just know that it is on the other direction. That's all. Okay, so this is something you need to do. For the example with visible thinking, please go and look at it yourself. If you are not sure, please ask your tutor.